musical instrument. Those are empty containers here that have beads inside. And when you shake them, they make that's a maraca. Okay? So it's a container with something in the inside. Okay? Those are buckyball maracas. I asked a question because when I gave this talk first time a few years ago in mainland China, nobody in the audience had an idea what a maraca was. Okay? And you will see why I call these things buckyball maracas. I assume everyone knows what a buckyball is. Right? Buck means the Fullerene or a carbon cage. And all of these that you see here are carbon cages, but all of them have something inside, as you can see. So you see the carbon cage and something inside, something inside. I selected this. I'm going to tell you this story today because this was the postdoctoral work of Professor Chen, who worked with me for 3 years. So this is going to be part of my story today. Okay? So we're going to be talking about all of these, by the way. All of these are crystalline structures. And nowadays you need to say this because you can draw beautiful things and they are not necessarily true. The sad thing is that some people just draw them and believe that they are true, right? And they are not really derived from crystallographic data. All of these are crystallographically determined structures, and we're going to be talking about many of them. Okay? So the plan is I'm going to tell you a little bit about mainly uranium. So we're going to be talking about actinide endohedrals. These compounds are collectively known as endohedral fullerenes or endohedral buckyballs, where you have a cage and something inside. But something doesn't have to be a single atom or a single uranium. It can be more than one atom, like in this case there are 4 atoms, 2 carbons and 2 scandiums, or in the case that I showed you before, here, you actually see 2 uraniums and a carbon. I'm going to be telling you the whole story, and I'm going to try to convince you that these stories are actually interesting and very important from very fundamental point of view. This is very fundamental chemistry, okay? So if you're an applied individual and you like engineering, you're in the wrong group. You can go somewhere else, go outside and catch the sun, because if you ask me what are these compounds good for, the answer is, I don't care, right? Because they are not made with an application in mind. These are not applied compounds. These compounds are going to tell you something about fundamental aspects of bonding and structure, as you will see. Okay? So this is my my plan, and I always like to start by giving credit to the first article. Can people in the back see this thing here? You need to stop texting, so, right? So texting is not allowed until I tell you. Okay? Whenever something boring is coming, I will say, okay, you can text. But in the meantime, nobody is allowed to text. Okay? So this paper in Nature in 1999 was published by Harry Dorn and his people. It's a very fundamentally important article in the world of endohedral forms. And the reason is, they show, this is serendipity at its best. And serendipity means they were not looking for this. They stumbled upon this. This happened to them, right? So they were actually trying to prepare inside an arc reactor. This is a typical arc reactor with 2 graphite electrodes. One electrode contains a hole, and in the hole they had scandium oxide. Okay? And they were trying to prepare scandium inside. This symbol hat means inside the C82K. That's what they were looking for. But they didn't find it. What they found primarily was this peak at 1,109 mass units. That for a long time, for 5 years, they had no idea what it was. Okay? And they just reported it. They saw it in the mass spectrum, and they were getting a little bit of this, a lot of this, and a little bit of this always. And finally, what they found was that there was an air leak in the system. This is supposed to be under 200 millimeters of helium, but there was a leak, so air was getting inside. And with air comes nitrogen. And with nitrogen, you have the possibility of forming other things. Okay? And what they discovered was that they were getting a scandium nitride, or 3 scandiums connected to a nitrogen cluster. So this is the first of the kind. This is called a cluster fullerene, because it doesn't have just 1 atom or 2 atoms inside, it has a cluster of atoms. atom. Inside either icosahedral or D5H symmetry C80 cages. Okay? This is the crystal structure. Beautiful thing, by the way. The way you discharge this, you apply high current. The high current vaporizes the graphite with the scandium oxide, and you end up producing a plasma. And these compounds are formed within the plasma. Okay? And the nice thing about this is, who is the best inorganic chemist here? Nobody can prepare scandium nitride. Okay? Scandium nitride does not exist. Not even the best inorganic chemist here. Okay? Who is the best organic or Fullerene chemist here? Well, icosahedral symmetry C80 or D5H C80 do not exist empty. Okay? They have been detected, but you cannot isolate C80 icosahedral symmetry or D5H. However, this one inside of this is the third most abundant Fullerene that can be prepared. So if you remember anything from this talk, remember that. This is not a curiosity. This is not a milligram. This is, you can make grams and you can make kilograms from this compound. And the beauty is, you have stabilized something that is impossible to prepare outside of the cage. But one and the other one is a perfect marriage. Is that clear? Say yes, even if you have no idea what it is. Sure, it's very clear, right? So, this is really the idea of using these carbon cages as nano containers or nano flasks. In other words, you can make things inside of these cages that you literally cannot prepare on the outside. And that's going to be the theme of my talk today. Okay? What are we going to incorporate inside of these cages? It's going to be quite unique and quite interesting. So that, if you want, is the hypothesis of my talk. Can we prepare strange things that cannot be prepared on the outside? Okay? So I'll give you more details as we go on. So in the world of actinide endohedrals, or uranium inside different cages, and diuranium inside cages, was published by Rick Smalley. I guess everyone knows he shared the Nobel Prize in 1996 for discovering buckyball. And he published this science article in 1992. Typical Smalley, what he did is he took graphite and he put uranium oxide. There's some people that are absolutely obsessed with texting. It's unbelievable. It's like an addiction. And what he did is he actually banged the surface of this material with a laser, and then he saw what came out of the surface. And he observed, very interesting, single uranium inside C28, C36, C44, C60, and so on. And I will show you later that he also detected diuranium species. Of course, typical Smalley, he's really a physicist, he didn't do any experimentation beyond this. So this is a classic paper, Science 1992, and from here on, theory people come in. Are there theory people here? Oh, come on, there must be a theory in this place. No. Theory people had a big time calculating every possible structure and this and that based on this article. But experimentally, very few people did anything. And the reason for this is, when you mention uranium to people, what is the first thing that comes to mind? Radioactivity. Atomic bombs, you're going to blow up, radioactivity, and so on. So no one likes to do this kind of work. But what people don't know is that uranium in natural abundance has radioactivity, but is nothing to be concerned about. Unless you drink and eat a whole bunch of uranium salt, it's actually not difficult to operate in the laboratory with uranium. It turns out that EHS people, the health people, they get all upset when you say uranium. Oh, you have to clean this, and they come with a Geiger counter. Oh, there's a little bit here. It doesn't really hurt anyone unless you really have breakfast with uranium oxide, which you don't, right? Normally. Anyway, experimentally, only 2 articles were published by Nakahara et al., one in JACS in 2001, where they pretty much isolated some endohedrals using a 2-stage IOC. They isolated this U2C80. This is the only data they report. And that's a UV visible. Can you see any information in this? If you can, let me know what you see, because to me, it's absolutely no information at all. And the uranium inside C82, you do see some structure, and they assigned it to a uranium with a charge of 3+, based on some comparisons and some calculations as This is all the experimentation that have been done since 92 until 2001, and even until last year, 2017. So here we go. This is our work. So we have been able to, using the same technique of arcing with uranium oxide, we've been able to isolate all the ones that you see in blue, all the ones that you see in red. We have been able to isolate, purify, characterize, and I will be showing you some crystal structures of these compounds. And interesting things happen with actinides that do not happen with lanthanides or with transition metals. And we're beginning to understand what's going on, okay? So the first thing that we did was actually isolate this uranium C74, two isomers of uranium in C81, isomer 1 and isomer 2. And you can see here the purification by HPLC, and then the mass spectrum, the multi-mass spectrum observed and calculated spectrum, so fully characterized and fully separated and purified, okay? And by the way, for those of you who do not know much about endohedral fullerenes, the easy part is preparing the things. The difficult part is fishing them up. So you end up with a whole bunch of things, and that's good because you end up with more than the price for the price of one, right? You end up with 10, 20, 50. The problem is now you need to separate them all, and that is the real difficult part in this business. So we purified all three. Here the UV visible, but that's really not the important part. We were able to solve for the first time crystal structures of uranium. Okay? And here are the three crystal structures for the compounds that I showed you. I am simply representing here the most abundant disordered position of the uranium. So in these endohedral, almost always you see a little bit of disorder in the cage, sometimes no disorder of the cage, but you always see disorder of the uranium positions, right? So I took a piece of the cage out to make it clear. It's not that it's broken, okay? This is a complete cage. I took some carbon so that you can see that we have quite a little bit of disorder in the uranium position, okay? Here as well. This one is disordered, but kind of different, right? I hope you see that this one is disordered kind of in a circular pattern. Something is different about this compound than these two. And I will show you coming up shortly what's different, okay? Calculations are very important in this work. And our collaborator in Spain, in Tarragona, is Josep Poblet, and he's done beautiful work from beginning to end. I need to thank him because his calculations help us understand what is going on, okay? And here are the calculations that he did. So he does the molecular orbital analysis. He combines the uranium with this 6 electrons with the D3H C74. We know the symmetry from crystallography, from the crystal structures that I showed you earlier. Before anyone asks, I forgot to mention, this is a crystallographic trick. We put a nickel octaethyl porphyrin as a co-crystallizing agent, and it makes crystallization much easier. So forget this, right? This is just there because we put it there to help us crystallize the compound, okay? So don't agonize over the nickel octaethyl. People sit there and go, what the heck is that thing in the bottom, right? It's not of your concern. So calculations show very clearly here, and I'm going to go very quickly, that of the 6 uranium electrons, you end up with 4 of them that localize pretty much in the molecular orbital of the compound. You end up with pretty much cage-based orbitals occupied by 4 of the electrons. So formally, there is a 4-electron transfer from the uranium to the cage. Okay, that's always, pretty much always the case when you make endohedral metallofullerenes and cluster fullerenes. You always have a very pronounced charge transfer from the cluster or the atom to the cage. Okay, so formally this is a 4-electron transfer, so you end up with 2 electrons that are mainly localized, as you can see in the uranium. These 4 are fairly delocalized over the cage. Okay, so formally this is really a uranium 4 plus C74 4 minus. Are you with me? If you get bored, let me know. Okay? If you get bored, I can do it. I can go faster. I can really motivate you. I can try to motivate you. Now let's do calculations for the other 2 C82 compounds. Right? So this is a C82 with C2 symmetry. And as you can see, the situation is very similar. From the 6 uranium electrons, and someone this slide is the fact that I draw some electrons red and some black, right? Electrons don't have color. I'm just tracking where the electrons came from, okay? I had a reviewer, and I think I know who that reviewer is, and I think Shai knows him well. He really gave us a heck of a time saying, electrons don't have color. We know that, but this is actually just for illustrative purposes, right? So you end up with, again, a formal 4-electron transfer to the cage, and you end up with 2 on the uranium. So again, formally, a 4-electron transfer from the metal to the cage. However, the situation for this isomer, which is a C2V symmetric C82 cage with a single uranium inside, the situation is different. Of the 6 electrons, you end up with 3 that are transferred to the cage. But you end up with 3 of them that are still localized, primarily on uranium atoms. The conclusion is that this one has undergone 3 electron transfer from the uranium. So you have a 3+ orbital oxidation state for uranium, and the cage is 3 light. And the reason for this is the proximity of the uranium to the cage, which interacts very strongly with particular orbitals on the surface of that C82 isomeric cage. Okay? So we understand what's going on. This is unique. So for the first time, and we published this last year, by the way, you're seeing the first ever crystal structures reported for uranium in the middle of bonds. Okay? So these were the first ever in the literature. And it's now about a year old. So not only do we characterize for the first time the compounds, we understand the bonding subtlety differences between isomers. So 2 different isomers of C82 lead to differences. So here's the conclusion, right? So you end up with uranium-4 in the case of C74 and this isomer of C82, and you end up with uranium-3 in the case of the other isomer of C82. Quite important and interesting because then you can modify the oxidation states of metals by simply changing the isomeric nature or structure of a cage. Okay? More recently, and this fortunately has just been having so many problems. We recently were able to isolate uranium inside a C76 cage and uranium inside a C80 cage. And this is really very interesting. So if you're texting, stop and pay a little bit of attention. I will give you a break for texting shortly. Okay? But this is important. So what you see here, separation pure by HPLC. By the way, we always use a recycling HPLC. And Professor Chen here is an expert. Do you know what a recycling HPLC is? Basically, what I tell you is that the effluent is, so you inject, it goes through the column, so you do minimal separation, but then whatever comes out, you re-inject. And you do this several times. It's more complicated than that, because when I was buying our Waters instrument in Texas, I called Waters and I said, do you have something equivalent to a recycling HPLC? A typical salesperson, sure, of course. Anyone can do it. It's just taking it. And then 3 days later, he called me and said, no, we cannot. So it's very exclusive. There are tricks. And this is mainly from a Japanese company. I think now Shimatsu also is manufacturing and selling an instrument. But anyway, it's fantastic. You can separate things that are very, if you don't have a recycling HPLC, you need to buy one. Okay? Because it is actually not that much more expensive than a regular HPLC. And you either turn on the recycling or not. You can use it as a regular HPLC or not. And you can take something that you can barely see a shoulder, and you can separate this baseline after 5, 6 passes. It's really fantastic. Okay? So anyway, we've done not only the uranium inside this is 76 and C80, we actually have done also the thorium. So this work is done in collaboration with an ex-postdoc of mine named Chen, who now works in Suzhou in northern England, China. And I'm happy to say that this is dramatic. It was just accepted in Japan. Okay? This is really I think very interesting and fundamental work. And why? Why is this interesting and different? And the reason is that for the first time on C80, you see what is known as a violation of the isolated pentagon rule. Okay? So this is the second thing you need to remember from this talk. When when you deal with empty fullerene, there are no known exceptions except functionalized from outside or from the inside. There are no exceptions to the so-called isolated pentagon group. That means that pentagonal groups on the surface of an empty fullerene are always adjacent to 6-member rings. So 5-member rings are isolated from each other. You never see 5-5 fusions. Clear? So now you know two things. At the end I have a quiz. Okay? So you need to remember all the things I'm telling you to remember from this talk. Because I have a quiz, and if you fail, there are very serious consequences. Okay? So what you see here in blue is a violation of an isolated pentagon rule. So you have two 5-member rings fused together. You see another one here, and you see another one here. So in the C76, definitely a violation. And you can see that in this case, the uranium is very, very close and pointing to that pentylene. A pentylene unit. Remember your organic chemistry, two 5-member rings, you have a pentylene, it's not aromatic, you give 2 electrons to it, and it becomes aromatic. You don't remember that? You can, well, that's number 3 question for the quiz later on. Okay. So this state is stabilized by electron transfer from the inside, the usual story that I showed you earlier. The same thing for the thorium and for the uranium, and interestingly, the cage that is selected is C1 symmetric, very low symmetry. Okay. So these compounds are chiral, all of them. Never seen before. First time this is seen, first time this cage is seen at all. Okay? And why is this happening only for uranium, right? It's only happening for uranium, or actinide. And the reason for this is quite interesting. The interaction that you see, this is the compound in C76, there is only one other violation of an isolated pentagon rule on C76, and that was reported for samarium by crystal structure. Okay? So this is the only other violation of an isolated pentagon rule. This one, as you can see, is interacting very strongly with the pentylene or with the 5-5 fusion, and the reason is there is a very strong covalent interaction. And this is the key thing. So covalency, in the case of uranium and thorium, is playing a much higher role than it does in the case of lanthanides and in the case of transition metals. So this is the secret to the whole thing. And it's a computation that has been done. These are all the bond lengths and distances, and the calculated interactions between the uranium and the cage clearly indicate a very high degree, not very high degree, much higher degree than in other atomic systems of covalency between the metal and the cage. So what are we doing here? We're learning very, very fundamental differences between the chemistry of actinides and those of lanthanides and transition metals. Okay? So very, very new stuff. This will be published in JAX very soon. So let me go back to the whole idea of what inorganic chemistry are we going to learn as we do these Endohedral. And my inorganic chemistry friends tell me that in actinide chemistry, there are 2 holy grails that people have been looking for 50 years. One is looking for actinide bonds, and the other one is authentic uranium double bonded to carbon. These have been looked for by millions of people in the inorganic community, and I will show you one that claimed that they had succeeded, but I will show you that they had not. And of course, I wouldn't be telling you the story if I didn't succeed. So I'll show you what we have done, that we have succeeded. So let me go to some calculations. This is Gagliardi in Minnesota, published in Nature 2005. This is all theory. And she predicts that the uranium-2 molecule in the gas phase should exist with a quintuple bond between the 2 uraniums with a dissociation energy of 30.5 kilocalories and a distance of 2.48 radians. What is known in terms of experimentation is essentially nothing. I hope that you can find something and tell me different, but all I can find in the literature is this paper by Gorovov and co-workers in a journal that I had never heard before in my life. It's called High Temperature. It's a Russian journal, and nothing against the Russians, but as you can see, this is old. This is 74. you can see that this is not a word processor. This is a typewriter. Can you see? The young people don't even know what a typewriter is. But, you can see very clearly that the letters are not lined up perfectly in a line, which means that this is a really, really old paper. There are no figures, but they claim that they took a sample of uranium oxide, they heated it at a temperatures around 25 to 2700 Kelvin. They see a mass at 476, which of course corresponds to uranium-2 molecule, 238, right? That's all that is that I could find in the literature to say that uranium-2 molecule should exist, okay, experimentally. Everything else is calculated. Now, other work experimentally by Soldier and so on, this is 97, they claim that they have done a uranium with hydrogens connected, and that this is the first, represent the first example of an actinide bond. How did they make this? They made it using laser ablation of uranium atoms with dihydrogen in a solid argon. Do you consider that a real molecule? In solid argon? Come on, right? I mean, that solid argon, I don't even know what the temperature is. That's cold as hell, right? So this is really cold to stabilize this thing. And they actually, this is not a crystal structure, they actually do it by calculations and infrared spectrum. So everything is inferred. There's no crystal structure for this model. Now you know what I'm going to tell you, right? I'm going to show you a crystal structure with one of these things coming up soon. Okay. So let's go back to the small. And I mentioned to you earlier, you can see that he also detected 2 uraniums inside C60, 2 uraniums inside 50, C58, and so on. So here's our work. Well, this is Gagliardi again doing calculations. Okay, let me tell you this on the next slide. Calculations say that uranium-2 inside C60 should form, but not very witty. They say the uranium-uranium bond is forced because of the cage is there. Okay. I kind of agree to some degree, but I have a problem with it. And the reason they do this is they now increase the size of the cage, and the uraniums move away. So uranium is kind of forced to interact. That's what they said. So it's an unwitting interaction. And sure enough, these other people, Straka and co-workers, they actually published this article in 2015 that says that indeed the uranium-uranium bond in C60, which is 2.74 angstrom, gets longer and longer and longer the bigger the cage gets. So whatever you see is that constant is that the uranium cage interaction seems to predominate over the uranium-uranium bond. Okay. So what did we do? This is a whole bunch of data here. This is pretty much everything that I can show you in terms of what data we get. You can see the whole sequence of mono-uranium, 88, 90, 92, 94, and so on. And it goes on, by the way, this way, and it goes this way as well. I'm just showing you the portion that I want to show because it is an important portion that I want to show. Okay? So, forget about the mono-uraniums. I already told you about the mono-uraniums. I want to point out the diuranium. So this is uranium-2, C72, uranium-2, C73. Doesn't that bother you? Cages don't come in odd carbon number, right? They come in pairs. So the C73 is something strange, right? And same thing here, uranium-2 C81, strange. Uranium-2 C80, okay. So let me tell you just the story of 2 of these compounds. The uranium, these compounds that we're detecting have never been detected before and have not been theoretically considered. For the obvious reason, theory people follow experiments. You tell them, hey, look at what I have, and then they go, and they calculate, that's the way it normally goes, right? And no one had ever detected any of these things, so they didn't calculate. They did calculate the ones for Smollet, but interestingly, the ones that Smollet detects are none of the ones that we detect, and vice versa. So they're mutually exclusive. We can discuss this in the question period if you're interested. I think I know the answer, but intrinsically, the methodologies are very different. Arc reactor, very different from laser ablation under high vacuum, but we can talk about it. So let me tell you the story of U2C80 first, very briefly, and the story of U2C81 very, very briefly as well. Okay? So what we see, isolation, the mass spectrum, theoretical experiment. found no problem. Not much information contained in the UV visible, a couple of little peaks here and there. But you see the color in solution. Now, I told you that other endohedral had very, very high concentration. You can make kilograms of it. You cannot make kilograms of this. You can make milligrams of this, right? At best. So, these are curiosities. But that's what my group is fantastic at, doing curiosities. And that's all we want to do. We want to see the fundamental properties of these compounds. So we succeeded in crystallizing this compound. And here's the crystal structure. And this was published actually this year in JACS. And you can see the two uraniums. You can see the cage. And again, you can see the trick, co-crystallization trick of nickel ortide with porphyrin. The people that do the theory, they have predicted that the distance between the uraniums would be 3.9 angstroms. And they call this article, the title is Unwilling Uranium Bonding in U2CA, right? So they really are pushing that the uranium doesn't want to happen. And what we have found is that the distance between the two, average distance, because there's a little bit of disorder here, a little bit of disorder there, the average distance is about 3.72 passes. Long, weak, so it's not a strong bond, but it's definitely stronger than the theory predicts. So we now have, and I think I showed you in the previous one, we now have U2C72. It's a case much smaller. So we're looking now at the isolation, crystallization, and characterization of U2C72. But more interesting than U2 is IC12. I would like to submit to you that this is an authentic uranium-1. Okay? Weak, long, but I think it is a bond. We can argue about it back and forth. Okay? These guys actually in the calculations did say that indeed there is a weak bonding interaction, even at this one. Okay? So let me go to the other one that I told you I was going to do. So this is U2C81, and the question you always ask yourself is it U2 carbide inside a C80 cage, or maybe even a U2C3 inside a C78 cage? What is it? Right? And here's, again, the characterization, separation, even the cyclic voltammetry is here, very uninformative, visible. But the nice thing about this is, I need to log this, it's now being published. I haven't seen that one. So the important thing is that we actually managed to crystallize this. Okay? Before I show you the crystallization, I need to tell you a little bit about uranium-carbon double bonds. Okay? And this article was published in JACS in 2009, and they made this very complicated ligand with uranium, and they claim that this carbon uranium is a double bond, and the distance that they measure crystallographically is 2.33 angstroms. Okay? Remember the number 2.33. Okay? Do you think this is really a uranium-carbon double bond? Say no. Obviously not, because I'm going to show you an authentic uranium-carbon double bond coming soon. This thing was actually featured by Polly Arnold in Nature Chemistry, and the title of the article, or the feature she wrote, is Now You See It. Very clever, very funny, right? That you see the double bond. So she claimed that for the first time, finally, they had a double bond. But I'm going to show you now that that was not a double bond. Okay? It's a real double bond you can see right now. So again, crystallize the material. You see a uranium, a carbon, uranium. This is just an expansion of this and one of the rings on the top and one of the rings on the bottom. So this is just a piece of this thing. And what you see very clearly, I think, is that carbon, uranium, the two distances are 2.0. So these are roughly 2 months, right? And theory predicts 2.02. So everything fits beautifully with the observation of the first ever well-characterized carbon-uranium double bonds. And not only do you see one, you see two. So the beauty of using nanocontainers of fullerenes is that you can stabilize things that have never been seen. This diuranium with a single carbon, this is the only monocarbide diuranium or dimetallic carbide with a single carbon. So this is the first everything. Nothing like this had ever been even thought about before. So it's really very significant result. So I would like to call it an authentic uranium double bond C double bond uranium cluster. So now you really see it. And you saw that article before, now you see it. Now you really see it. This is really a true double bond. And not only do you see one, you actually see two of them. This was just published about 2.5 or 3 months ago in Nature Communication. So we're very proud of this. And of course, the beauty of it is that we now have different things. We now have not only carbide, we have sulfide, we have oxide, we have nitride. And we're working on all of that. And not only on C80, we are actually seeing C78, C76, and C70. Okay. So we now have a whole bunch of stuff to probe the fundamental aspects of bonding between actinides and other atoms that have never been seen before. Thanks to the buckyballs, the nano containers that allow you to stabilize. Oh, by the way, I didn't mention this before. Remember the guy who did this in solid argon? These compounds are stable in air, in water, in everything. These are perfectly stable compounds. So they are not in any way reactive at all. Okay? So really fantastic result. So this is where we are with this isolation business. This is the molecular orbital picture, which is beautiful. You end up with 2 new F electrons, and then two center 2 electron sigma bonds, and then 3 center 2 electron pi bonds. So everything is fully understood and beautiful. I didn't mention anything about the angle. I don't know if anyone noticed that it's not linear. The prediction was that they should be linear, uranium, carbon, uranium, but it isn't. And the reason is that the carbon formally is 4 minus, and the uraniums are formally 5 plus. So there's so much charge on the carbon that it actually acts more like a carbenium, and it bends the bonds away from. So really quite amazing results. So let me just tell you something that we just published that we're kind of excited about. Excited because we don't like to do HPLC if we can avoid it. And the nice thing about this work, people have been making capsules to bind fullerenes for a long, long time, right? And I just put some AIDA's work and so on. Those are so. We've been working with this guy, Xavi Riva. He's in Girona, Spain. And he makes these bis porphyrin, so he puts a porphyrin at the top and a porphyrin at the bottom. And he puts these as linkers, so you end up with this crystal structure, either palladium as the binding metal, or with copper as the binding metal. And I will show you the results with the copper binding metal. What is the idea? The idea is this capsule selected to bind fullerene? And interestingly, the way people do this business in Supramolecular is they don't design a capsule to bind something. They design the capsule, and then they see if it binds anything, right? So they go fishing. They have a hook, and then they go, okay, let me see, is it good for C60? Okay, or C70, what is it good for? So that's exactly what we did here. And it turns out they are exquisitely selected for uranium inductors. And this is really nice. We just published this as well in Levante. As you can see from the soot, you end up with a whole bunch of different compounds. You put the solid state, and this is important, in the solid phase, you put the capsule inside the solution containing all of these, and that solid phase state is able to selectively bind only one compound, which is a uranium-2 inside C8. And you can filter, and you can quantitatively separate. Look at the mass spectrum. You start with uranium-2 C80 and all of these things, and you selectively eliminate it completely. Then, using a solvent technique, you can just release it, and you end up with pure uranium-2 C80. How is that? Not using HPLC. This is fantastic. So we can now purify some of these compounds without using HPLC. We're very, not only is it practically useful, but we're learning a lot about the specific interactions. Why does it select uranium-2 at C80 over, for example, this compound, which is also there, scandium-2 uranium carbide at C80? And it turns out, if you keep adding to the remaining solution, so the solution now you have eliminated this one, but you have the remaining everything else. You keep adding more solid capsule. And what you see is now the selective complexation of scandium-2 uranium carbide until it disappears, and then you can release it as well. So we have purified 2 compounds without HPLC sequentially using no HPLC at all, which is absolutely fantastic. So we're really very excited and looking forward to further purifications. This supramolecular interactions of capsules with uranium intermediates. Okay? And we're learning a lot about that. So let me shift gears now to tell you a little bit about mechanistic aspects of the growth of these cages. Before we started working, this actually was published by Prof and Lunch a long time ago. These are dimetallic carbides. So these are the tetra, di, tri, and tetrametallic carbide endohedral cluster fullerenes. A whole bunch of them were known before we started this work. This is the work of Professor Sam here. These were known in C72 cage, cage 284, but he was able to isolate very nicely scandium-2 C88. And the first question you ask is, at least 2 scandiums inside a C88 cage, or is it scandium-2 C2 inside a C86 cage? And here is the exact photometry, all done by Echegoyen. Visible, purification, mass spectral movement. Okay? But the nice thing is that we got a crystal structure for this. And the crystal structure showed a cage that at the time had never been seen, a C2B symmetric C86 cage. Here it is. You can see the scandiums are fairly strongly interacting with the cage on both ends. And you can see that the carbide, the 2 carbides, are elongated. So instead of having what they call butterfly shape that looks like this, it's a fairly elongated scandium carbide because of the interaction of the scandium. And the nice thing about the structure is the cage is fully ordered and the scandium carbide is fully ordered. So this is a fully ordered structure, no disorder whatsoever. Okay. Is this a nice thing? Well, this is now, wow, you were there a long time ago. Back in 2015 we published it. But this is not the most interesting part of this work. Out of the same soot, out of the same experiment, he was able to isolate a second compound, which is scandium-2 C90. And the question, of course, again, is the same thing. Is it, oops, sorry, I don't want to. You shouldn't have done that. You didn't see it, right? You did not see it. Everyone is falling asleep and texting anyway. So, this is the separation, and this shows you the pain of doing this, and you can talk to Professor Chen about it. This is what you start with. After you pass it through a specialized so-called 5-PYE column, and then you go on a second stage through another specialized Bucky prep. And then you go third stage on a Bucky plunger. Now you have used 3 different columns, right? And finally, you check, and sure you know how, by the way, recycling HPLC. So you start here, then you see a little shoulder here, rows, separate, voila. So you can actually separate compounds very nicely. You end up with pure compound, visible. But the nice thing is that the crystal structure was resolved. And this was a surprise. Okay, so this is serendipity. Okay, we were not looking for this, but we got it. Okay. Now, what do you see in the next slide that calls your attention? Just a hint. It's in blue. Okay. What do you see? Count the edges of this. It's a heptagon, right? So for the first time, we have seen in our lab a heptagonal figure. Is this a fullerene? Fullerenes are defined as carbon structures composed of 5 and 6 member ring carbon. This is not 5 nor a 6 member ring. So this is a 7 member ring. So officially, you cannot call this a real fullerene. Well, of course, it is a fullerene, right? Now, why do we get this heptagonal thing? What's a reason for obtaining this? And I want to give credit again to Joseph Poblet because he came up with a beautiful explanation for this, which I will show you in the next slide. So what he did is he took the C86 structure that we reported, and he took C2 unit, and he started putting it in different places, adding because there's a big controversy in Fullerene chemistry whether things grow bottom up or top down. The theory people favor top down. They say you arc, you have a whole bunch of carbons in the plasma, and carbons come out, and at the end, C6 or C7 or whatever. But other people say, Larry Croto started this school that, you can build things by addition of C2. So he found out that if you put that C2 exactly in that position, you end up with exactly the structure that I just showed you in the previous slide. But it's interesting. You do the calculation of the energy for that, and that is not the most stable species. That species could go to much more stable, but in order to do that transformation, you need to undergo either 4-bond or 5-bond rearrangements, so-called stone whales rearrangements, each one of which has a barrier, each one, of 140 to 150 kilocalories per mole. What does that mean? That means it doesn't happen, right? You're not going to have 4 successive 150 kilocalorie activation energy processes happening. So what we have, or what Echegoyen was able to isolate, is a kinetically trapped intermediate. So it adds there, it transforms into this, and then it's stuck kinetically. Because in order to go to the more stable things, it has to undergo 4 or 5 stone whales rearrangements. And it just simply doesn't do it. Okay? This was published back in 2016. It's a little bit dated now, 2 years ago. But it's one of my favorite articles because we really gained a lot of understanding about the mechanism, how these things grow. I think this is one of the most important papers in the mechanistic development of or evolution of these compounds. This has led to additional experiments we've done with the people in Florida State. We have given them starting materials that are pure. They have actually done in an ICR machine in the presence of carbon vapor to see if they grow. And sure enough, you start with this pure compound, and you can see addition of 2, 2, 2, 2, 2, 2. So you can see the growth pattern. Notice that you do not see the removal of C2, C2, C2. So top down doesn't seem to be working. Bottom up seems to be working really well. Okay? And this led, this is a Nature Communication last year, and led to this very complicated scheme that allows you to predict if you start with a D3 symmetric C68, you can actually transform this very nicely by C2, 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 C2 additions into a C80 of the polyphasic symmetry. So it gives an idea of the topology and the mechanistic aspects of how these compounds are growing. And we have additional data now. This work is going fantastically well. Okay? We're really very, very happy with this. So we're beginning to understand. How am I doing for time?
Very good.
I'm doing okay? Okay, then let me finish. I will go very quickly through the functionalization. So this is the other part. This is the famous C80 icosahedral symmetry. And the chemistry that you do on fullerenes never say substituted fullerene, right? You don't substitute a fullerene because you add to double bonds, right? You don't take a carbon out. If you do take a carbon out and put something else, okay, so you substitute something. But if you just add to a double bond, you're doing addition chemistry, and these are adducts or additives, not substituents. Okay, you didn't substitute anything. So there are only 2 types of double bond or additions in icosahedral symmetry C80, so-called 5-6 double bond or 6-6 double bond. So all the chemistry that you do, addition chemistry, is either 5-6 or 6-6. Okay, and I want to tell you, our first article is now really old. We published this back in 2005, so sorry for showing something, but just to put it in perspective. Now what you see is that changing, we're very interested in what is the effect of exohedral chemistry. I am an endohedral fluoride. Okay. Exohedral chemistry due to what you have in the inside, right? Is there an interplay? They should be, right? Intuition tells us, of course, there should be some electronic interaction. Actually, I'd like to tell people that this is relevant to graphene. Because when you take a single graphene sheet and you put it somewhere, whatever you have on the other side is going to influence whatever. It's just this single molecular layer of carbon, right? And here you have very, very well characterized single molecule, single layers of carbon. Anyway, well, we saw changing from scandium nitride inside to yttrium, just one down in the periodic table, just one down. You go from addition that is exclusively 5,6. How do we know? Because we only see one carbon, 13 label, in this reaction which forms a pyrolytic. So that pyrolytic is in a symmetric environment. How do we know? Because we see only one carbon. Now you go from scandium to yttrium, and now you see two, one of which coincides with the same chemical shape as here. So that must be the one that is sitting on top of the 6-member ring. And that one must be this carbon sitting on top of the 5-member ring. This may be a good time to text. Okay? It's getting complicated, right? So are you following all the details, or are you falling asleep? I find this fascinating because just changing the nature of the inside metal from scandium to yttrium completely changes the regiochemistry of the exohedral 1,3 dipolar cycloaddition reaction. Okay, quite spectacular. So we've done a lot of mono additions of everything. 1,3 dipolars. We've done addition eliminations. We've done 2+2 additions. We've even done electrosynthesis and so on. We've done quite a bit, but always one single addition or atom. Right? We understand how to put one atom on these endohedrals reasonably well, and we can actually even predict where they go. I don't, but my colleague from Spain, Mikel Solá, he does a whole bunch of calculations. I don't want to bother you with the details of this, but he can actually predict exactly where the first and the second atom will go. We were very interested in putting more than one. We were interested in putting two atoms. Okay? We've also published things like this where we end up with C68 and nitride, and we're able to predict very nicely where the addition is going to take place. Okay? Crystal structure and everything like it. So, what happens when you put two, and how many methodologies are there to put two things in a controlled manner on Fullerene? There are only two. First one is very specialized. I'm not even going to discuss, okay? Which is the one reported by Bernie Kreutler back in 1996. It's a very unique case and very specific, so I'm not going to mention it here. The general method is a tether-directed multifunctionalization. This is very general. What this says, it's a big word for you take something, a tether, a piece of something, and you put two reactive groups at the two sides. And you control the size and the rigidity of the tether. By doing so, you can go onto a Fullerene and put the two reactive things where you want them, not where they want to go. So you do not get isomerism. You control the isomerism by controlling the tether. Okay? This is a beautiful example we published together with Fullerene, where you have a dibenzoate in chrome 6, and what happens is it adds only exclusively trans 1. Trans 1 means double bond here, so this here is a double bond, and the other double bond is exactly in the other side of the C system. Okay? Regio selectively pure. You don't get any scrambling over this addition. Okay? Very elegant. We've done a lot of this. I can show you here reagents with diazo compounds that give you only one isomer on C60, cis1. This one gives you this bingo atom or addition elimination, cis2 only, trans2 only, and so on. So they work beautifully. Only one item. Fantastic. So let's do it with endohedral. Right? Right? And I should have thought about this before I told the students to do this. But we tried the same reagents on trimetallic nitrides. And guess what happens? None of them work. And what does none of them work? Students always come and say, don't work. What the hell does not work mean? Right? Did you get the reagents back? If you get the reagents back, okay, it didn't work. But if you see something happening and the reagents have disappeared, then something happened. And I would like to know what happened. Right? And what happened was, in every case, you would get one addition, but the other one would not happen. What is that telling you immediately? Think about a second. That must be telling you that what's inside has some control on what is happening outside. So we decided to do this. I blame myself. The experiment we should have done before, which is, what if we put independent groups. So forget the tether. The tethers don't work. So what about non-tether? So can I put two wherever they want to go? Right? Forget. The tether is not controlling. Evidently only one goes, the other one doesn't go. So what if I put two? Will they go? And the answer is they do go. How many isomers do you think are possible? If you put two groups, two pyrrolidine groups on a C80 icosahedral symmetry cage. There are 91 possibilities if you allow for additions on 5,6 and on 6,6. So you end up with 91 possible isomers. So we do the experiment. How many isomers do you think we get? Just take a wild guess. Oh, come on, you can't go wrong, right? So we only see 3 in the case of scandium nitride. Out of 91 possibilities, right? We're only seeing 3. Who's controlling those 3? It has to be the scandium nitride, right? It's telling you put one on, which typically, not typically, always goes 5,6. And the second one goes wherever the group inside tells it to go. And you only see 3 of them. Beautiful, this is a beautiful work. It's one of my favorite ever articles from Maida Ceron. Absolutely spectacular work. To the force, because we were, the molecules that you get is chiral, and the NMR, I had never done chiral stuff with fluorines, and we didn't know for a long time what the heck was going on. Professor Chen helped us a lot with this. So, in the case of lutetium, you only see 2 out of 91. So obviously a very reduced number. What do we learn from this? What we learned, again via calculations, is that after you add the first pyrrolidine on the 5,6, the second one is favored by the positioning of the group inside, which adopts this conformation. And what happens is that that metal, or scandium or lutetium, pushes these 2 carbons a little bit up, makes them a little bit more pyramidal. This is the pyramidalization angle calculated for 11, 29, 19, 39, 11, 29, 19, 39. And as you can see, they're more pyramidal than the rest of the carbons. Including these, it's not as clear, but you can see the C78 and the C65 in the one. So theory predicts clearly where the second group is going to go, which is where more pyramidalization is, which is where you have the most strain, and that's what you do. You react there to release the strain on the gauge. So I think this is good, because now we understand at the very fundamental level what's going on. And I don't bother you anymore. I think this is it. Do you want me to summarize, or do you want me to just skip it? Uranium endohedrals, you can change the oxidation state based on the cage. Non-metallic endohedrals are amazing. We're working now with C72 and C78. The famous U2 carbide inside is something we absolutely did not anticipate. Now we're looking for those inside the different cages. And as I mentioned, we now can do nitrites, like uranium nitrides, oxides, sulfides, also in different cages inside, especially the 678. The capsules promise to be a very good way to purify these materials without HPLC. And the endohedral fluorines show you the mechanistic perspective of how these things are actually growing using a bottom-up approach. And the traps, or the clusters trapped in the inside of these things, regulate the regiochemistry on the outside and limit the number of bismuth that we perform. I think that, well, I gave credit to Solar, Silvio Osuna, who was the one who calculated the last thing that I mentioned, and her student work. Javi Rivas is the author of the capsule. His 2 graduate students. Joseph, I mentioned more than enough, I think. He's got a lot of credit. He's fantastic. He's not able to be able. And his group, these people here. Ning is my ex-postdoc. He's actually collaborated with us in all of the actinide and fluorine work. And in my group, Wenting Kai is the author of all the uranium endohedral in my group. And some undergraduates, Jesse, Daniel, a colleague of mine, Sky Fultia, he's an expert in actinide chemistry. Additional people, and of course, here is Chen, author of the peptidral fluorine. that's the only day during that whole year where there were clouds. Normally, there are no clouds in the sky. It's always blue, intensely blue, almost painfully intensely blue. Okay? The people who fund their work has been mainly the National Science Foundation,